Okay, now in section 1.6, there's several graph operations. There's the join, there's the sum of two graphs, and what I want to focus on is the hardest one, the Cartesian product of two graphs. So we denote that with like a G and then a funny square symbol and then an H. So when I read this, I'm just going to say G times H. It has the vertex set V of G, Cartesian product V of H. So this is the standard Cartesian product of sets, meaning that this consists of all ordered pairs where the first part of the pair is a vertex from G and the second part of the pair is a vertex from H. And so the vertices of G times H, their names look like this. So if U is the name of a vertex in G and V is the name of a vertex in H, then there's a vertex in the product graph, G times H, whose name is this. It's an ordered pair where the first part is a vertex in G and the second part is a vertex in H. And the way we talk about the edges is, so let's say I have a vertex whose name is this in the product graph, and say another vertex whose name is this in the product graph. So of course this means that X is a vertex in G and Y is a vertex in H. So these two things are going to be called adjacent in the product graph if we have one of the following. Either U is the same as X and V is adjacent to Y in the graph H, or V is equal to Y and U is adjacent to X in the graph G. So I'm going to illustrate this. There's some illustrations in the book, but I'm going to give a different illustration. Let's do the product of these two graphs. Let's do G times H. So here I have a graph G. It's just this triangle with the vertices A, B, and C. And here I have H. So I even started already. I didn't finish, and I already made a little mistake. But here's how I would start. I'm going to draw a bubble for each vertex of H, the second graph. So H, in this drawing, it's got a vertex here, 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 and here. They're sort of arranged in like a square. So here I made like a square of bubbles. So each one of these bubbles is sort of corresponding to a vertex in H. Inside of each bubble, I draw a copy of G. So inside this bubble, I drew a triangle. Inside this bubble, I drew a triangle here and here. And now let's talk about the names of these vertices. The names of the vertices in G are A, B, C, and this bubble is corresponding to the vertex whose name is 2 over here. Oops, my alarm's going off. There we go. This bubble is corresponding to this vertex here. So that's why these three vertices, their names are A, 2, because this is the vertex corresponding to A here, and it's inside the bubble corresponding to 2 here. So it's A2, B2, C2. Similarly, this is the bubble corresponding to vertex number 3 here. And so this is going to be A3, B3, C3. And so this down here would be, I guess this bubble is corresponding to 1. So A1, B1, C1. And this is 4, so this would be A4, B4, C4. Maybe I won't write that. Now I'm not done. There's going to be more edges. So I would say that so far So far, the edges that I've drawn are all like this, because this graph is supposed to have two types of edges. They're the edges that are described here and the edges that are described here on the second line. And so far, I've drawn the edges that are on the second line. Let me help you make sense of that, I guess. So the second line is when v equals y, and that's like when this second coordinate equals this second coordinate. Just like, say, these two vertices. They have the same second coordinate. The second coordinate is both 2. So the second coordinate is 2 and 2, and I draw an edge here because 2 and 2 are the same, and B and C are the names of adjacent vertices over here. But there, and that's similar for all of these edges that I've already drawn. But then there's the other type of edge. There's the edge where the first coordinates are the same. So u equals x, and then vy is an edge of h. So let me start slowly here. Let me think of an edge of h. So there's an edge from 1 to 2. So in this picture, there should be an edge in between any two vertices that have the same first coordinate. Like, let me pick two vertices like these two, A1 and A2. Yeah, that's perfect. They have the same first coordinate, and the second coordinates are 1 and 2, which are adjacent vertices here. So I'm going to draw like the edges of the first type are in black, and the edges of the second type, the ones that I've already drawn, are in black, and the first type I'll do in red. So this should be adjacent to this. Similarly, here's B2 and B1. The first coordinates are the same, and the second coordinates are 1 and 2, which are the names of adjacent vertices in H. So this vertex should be adjacent to this vertex. And then C2 is adjacent to C1 for the same reason. So basically what you see here is I have like this triangle, and like the top vertex has an edge to this top vertex. The vertex on the bottom left has an edge to this vertex on the bottom left, and the vertex on the bottom right has an edge to this vertex on the bottom right. And that's what we're going to see more of. For example, I'm going to have this, and this, because I went from B to B, A to A, and C to C, and also because the vertex 2 is adjacent to the vertex 3 in H. And I'll go faster. Basically what's going to happen is I'm going to keep doing this for each edge of H. So I did the edge from 1 to 2, and then I just did the edge from 2 to 3. Let me take care of the edge from 3 to 4. Here's 3 and here's 4. I find the corresponding bubbles. So here's the two bubbles, and then I just do this. I'm going to attach the top to the top, the bottom right to the bottom right, and the bottom left to the bottom left, just like that. And there's more. There's the edge from 1 to 4. So I go top to top, bottom left to bottom left, bottom right to bottom right. And then there's one more edge. Of course, yeah, unfortunately when you draw this it just turns into a mess. So it'll be helpful for you to watch the video, because it goes from being less messy to, by the end, it's already a mess, and it's about to be slightly messier, but I'm almost done. So in the end, when I scan this, all you're going to see is the final mess, but as you watch the video, you'll be able to see me forming it. I haven't taken care of this edge, so I have to look at this bubble, and between these two, I've got to go top to top, bottom right to bottom right, and bottom left to bottom left. And I have no choices here but to make a mess, so I'm just going to do it. So that's how you draw the product of two graphs. So let's prove something about this. This is not an exercise in the book. This is something that I just, well, I'm sure somebody's done this before, but I just kind of made it up. Let's prove that if G1 is R1 regular and G2 is R2 regular, then G1 times G2 is R1 plus R2 regular. So this is, I wouldn't describe it as a hard exercise, but you do have to kind of understand and interpret the definition of Cartesian product. In essence, what we're about to do is pretty simple. Like we're just assuming that every vertex in G1 has this degree, every vertex in G2 has this degree, and then I just have to show that every vertex in this has this degree. So let's consider a vertex in this graph. And before I go giving it a name, let me think about what the names look like. The names in a product graph look like this. They're ordered pairs. So maybe I'll call it, say, V1, V2. Be a vertex in G1 times G2. So V1 is a vertex in G1 and V2 is a vertex in G2. And we just want to find the degree of this vertex. So finding its degree means finding the number of neighbors. It's the number of other vertices that it's adjacent to. And here we have the rules that tell us when vertices can be adjacent in the product graph. And there's two types. So let's break it down by type. So there's type 1 edges, which is where the first coordinate is the same. So actually, I'm going to leave a little blank here that I'm going to fill in later. So there's the first type, once again, where the first coordinate has to be the same. So we're talking about a neighbor of this vertex, V1 and V2. And we're talking about another vertex whose coordinate has to be the same. So let me just fill in a V1 here. And then what can the second vertex be? Well, I'll just put an X there. Wait, actually, maybe that's confusing because I used the letter X somewhere else. Let me say, I don't know, B. And right, going back up here, the first coordinate has to be the same, and the second coordinate just has to be, it just has to be something that's adjacent to H. In other words, in order for this vertex to be a neighbor of this vertex, we already made sure that the V1 is the same, but what we also need to make sure of is that B is a neighbor of V2 in H. Okay, now let me fill in this blank. How many choices for B are there? Well, B has to be a neighbor of V2 in H. How many neighbors does V2 have in H? Well, every vertex, oh, whoops, I meant G2 when I wrote H. Yeah, okay, so let me repeat. How many neighbors does V2 have in G2? Well, every vertex in G2 has this many neighbors. That's the degree. So there's R2 neighbors of this. And you can probably guess how the rest of this is going to go. I counted the neighbors of one type, that was this, and then I'm going to count the neighbors of the other type, and we know that we're going for a total of R1 plus R2. So, and we already have our R2, so the next one's going to be an R1. But let me not jump so far ahead. And a total of R1 neighbors of the form, the other form, where the second coordinates are the same and the first coordinate has to be a neighbor. So if I'm looking for a neighbor of this, then the second coordinate has to be the same, so I'm going to fill in a V2. This is just how, like, when I was doing the first kind, I filled in the first coordinate with a V1. Now that I'm doing the second kind, I'm going to fill in the second coordinate with a V2. And the first coordinate could be whatever. I'll say A, where A is supposed to be a neighbor of V1 and G1, where A, V1 is an edge, edge in G1. And indeed, there would be a total of R1 of those because every vertex has R1 neighbors in G1. And then, yeah, I think we can just put a proof box. We counted all the neighbors of this. Maybe I'll just write a short sentence summarizing this, but we're done. So V1, V2 has degree R1 plus R2, and that's true of any vertex in the product graph. So it's R1 plus R2 regular, and that's the proof. Okay. Then let me just talk a little bit more about these hypercube graphs, mostly just because I think they're cool and it's a nice way for me to keep talking about Cartesian products. So the hypercube graphs are called Q1, Q2, and then, you have Q3, Q4, all the way up to Q, well, they go forever, actually. But, so Q1 is just the complete graph on two vertices. So this is K sub 2. When you see K with a subscript, that just means you draw that many vertices, and they're all adjacent to each other. So here's a picture of Q1. Q2 would be, so you start defining them this way. So each Q sub n is like the previous Q product with K sub 2. So I'm going to take the previous graph and I'm going to do the product with K sub 2. So how do you do this? This is like I'm doing the product of K2 with K2. So I'm going to draw a bubble, and then I'm going to connect the top to the top and the bottom to the bottom. And then you can kind of start seeing why we call these hypercubes. Of course, the first one just looks like a line segment, and the second one just looks like a square. Q3 is going to look like a cube. If I do the product of this graph with K2, what does that mean? I'm going to draw two bubbles. Let me try to, so I'm going to draw, here's a copy of the previous graph in this bubble, and then in this bubble I'm going to draw another copy. And if you notice, I'm drawing it in a bit of a funny way. It's the same graph. I mean, this graph is just 4 vertices all in a cycle, and that's what I drew. But I'm kind of also trying to draw it so that you can see why we call these the hypercube, because what I'm going to do now is I'm going to draw some edges going across, and it's just going to be between corresponding vertices. So there's the, if I turn it this way, there's the vertex in the from this angle, it looks like the top right. So I connect the top right to the top right, the bottom right to the bottom right, top left to the top left, and bottom left to the bottom left. And that looks like a cube. Well, it's a bit elongated, but you know what I mean. It's like a three-dimensional box. And maybe I won't attempt to draw Q4. Well, okay, I won't really draw it, but if I try to draw it, it'll be a mess, but I can describe what you would do. I would take the previous one, I would draw a copy of it in this bubble. So it's like, if we use our imagination, I just put a copy of this graph in this bubble, a copy of this graph in this bubble, and then I would connect corresponding, like I would draw edges going across between corresponding vertices. Yeah, okay, so let's do a problem real quick about these, just about the order and the size of Q sub n. So first of all, let's talk about order. So that's the number of vertices. In general, the number of vertices in G times H is, it's easy, it's just the number of vertices in G times the number of vertices in H. Right, there's a number of ways of seeing that. First of all, the vertex set just consists of ordered pairs where the first coordinate is anything from G and the second coordinate is anything in H. So how many choices do you have? You can fill this in with anything from G and fill this in with anything from H. So it's just the number of vertices in G times the number of vertices in H. So basically, what we're going to notice off of this pattern is the number of vertices in Q sub n, because Q sub n is the product of these two, it's going to be the number of vertices in the previous one times the number of vertices in K2. K2 just has 2 vertices. So basically, the number of vertices just doubles each time. The number of vertices in Qn is twice the number of vertices in Q sub n minus 1. And if you look at the pattern, Q1 has 2 vertices, and then 4, and then 8. So these are just the powers of 2. Q sub n has 2 to the n vertices. So that's the order. Okay, so let's talk about the size of these hypercubes. Right, so here's how we're going to attack the size. Whoops, I have some stuff already written I don't want you to see yet. But here's how we're going to deal with the size. These, if you notice, they're regular graphs. Yeah, what am I doing? This is 1 regular, each vertex has degree 1. This is 2 regular, each vertex has degree 2. This one's 3 regular, and so on. So it's easy to guess that Q sub n is just going to be n regular. And then we'll use that to tell us the number of edges. So, right. So Q, and right, we just proved something about the product of regular graphs. If G1 is R1 regular and G2 is R2 regular, then the product is just is a regular graph, and you just add R1 and R2. So if Q1 is 1 regular and Q sub n is the product of something, if we assume that Q sub n is regular and this is also regular, and this is not even an assumption that this is always true. K2 is just this graph and it's 1 regular. Then Qn is just going to be whatever the degree of vertices in this graph is plus 1, because this is 1 regular. So Q2 is the product of Q1 with a 1 regular graph. So if this is 1 regular, then Q2 is going to be, well, it's the product of a 1 regular graph and a 1 regular graph. So Q2 is 2 regular, as we saw by looking at the picture. Q3 is the product of Q2 with a 1 regular graph. So Q3 would be 2 plus 1 regular. So Q3 is 3 regular. And I'm not going to do this formally, but you can prove by induction that Q sub n is n regular. If you assume that Q sub n minus 1 is n minus 1 regular, so you have the product of an n minus 1 regular graph and a 1 regular graph, so you would add n minus 1 plus 1 and you would get an n regular graph. So you can prove that by induction. Q sub n is n regular. So the degree sum, because what we really want is the size, which is the number of edges, and now I'm about to use the handshaking lemma. The degree sum is what? Well, there's 2 to the n vertices. Each one has degree n. And the degree sum is supposed to be 2 times the number of edges. I'm saying that there's m edges. So the size is just m, and I have to solve for it. So I'll divide by 2. It's n times 2 to the n minus 1, because there's a 2 that cancels. So there we go. That's the order and the size of the hypercube.